Hi class, my name is Lizhe Chen. Today I'm giving a real presentation of a paper on CVPR 2018 from the Google Brain team. The author is Barry Zoff and his co-workers. This paper introduced a reinforcement learning method to build the deep neural network architectures for image recognition tasks, both on the small datasets such as CIFAR, on the large datasets such as ImageNet. In recent years, deep learning has made a massive breakthrough in the field of image recognition. For example, in the ImageNet competition, models' recognition ability has surpassed humans already. However, the deep neural nets are often very complex, and achieving a successful image classification model requires a lot of engineering to design the architectures. Therefore, the team from Google has this idea: whether we can build an algorithm to learn the architecture of the neural networks automatically, which has equal or even better performance than the human design models. So they start a series of studies, including this paper, about neural architecture search with reinforcement learning. The proposed method is related to the previous work in hyperparameter optimizations. They are exploring optimal hyperparameter settings during the construction, such as the number of filters. Some groups also try to transfer the learned architectures from a small dataset, like CIFAR, to the ImageNet dataset, but their performance are notably below the current works. This paper also mentions the meta-learning approaches, which is a very new term. The goal of meta-learning is to use such metadata of the dataset to understand how automatical learning can become flexible to the different datasets in solving learning problems. In order to improve the performance of existing learning algorithms or to learn the learning algorithm itself. However, most of these metadata approaches have not been scaled to a significant large problems like ImageNet. The most previous work is neural architecture search with reinforcement learning, which with the main author are same person. Before the NASNet, the primary author Barrett introduced their neural architecture search framework in 2017. The goal of NAS is to find a suitable neural network structure for better generalization and performance on a type of task, in here which is image recognition. As shown in the left image, this NAS uses a recurrent network as a controller to generate the model descriptions in text of the neural networks. The model generation stops when reaching a fixed max layer number, which is set by the user. We can build a child network with a model description text. Then training of the child networks on the real data will produce an accuracy on a validation set. By using this accuracy as a reward signal, we can compute the policy gradient to update the controller agent. The NAS updates the weights in the controller using the reinforce with baseline, which is mentioned in our class. As a result, during the iterations, the controller will give higher probabilities to the structures that receive higher accuracies. In other words, the controller will learn to improve the architecture search over time. However, the main limitations of NAS is very obvious. It is very computationally expensive for processing image, even for the small size datasets. So NAS is not applicable to large datasets like ImageNet or even other convolution applications. And we cannot transfer the architecture we learned to another dataset. So we cannot transfer the architecture we learned, for example, in the CIFAR to the ImageNet. since both way is not workable. In 2018, Barrett and his co-workers carried out this paper, which is NASNet. The key contribution of this paper is the design of a new search space of the different convolutional cell structures. And this new search space enabling the transferability between different scales datasets and reducing the computation cost. Now we are talking about the method of this paper. The key insight is that many successful CNN network structures contain some repetitive structures, such as ResNet or Google Inceptions. In NASNet, the overall architectures of the convolutional nets are manually arranged. They are composed of different convolutional cells repeated many times, where each convolutional cell has the same structure, but different weights inside. Convolutional cells only have two types and they are learned separately. The first is a convolutional cells that does not change the size of the input feature maps, which is named normal cell. The second type named reduction cell, and this cell is used to reduce the height and the width of the input feature maps to half. We have more reduction cells on the ImageNet architecture, since the incoming image size is much bigger. Actually, it's 100 times bigger than the sci-fi images. And the parameter n here is a free variable for repetition number of the normal cells. When network structure is defined, the controller in NASNet predicts the detailed structures of the normal cells and the reduction cells in the prearranged layouts. The algorithm will search the structures within a special search space. In NASNet search space, each cell receives two initial hidden states named HI and HI-1, which are the outputs of the two cells in the previous two layers of the start input images. Given these two initial hidden states, the controller recursively predicts the rest of the cell structures. The NASNet groups the prediction of the controller for each cell into a number of B blocks. Each block has 5 different prediction steps made by 5 softmax classifiers corresponding to the choice of a block inside the controller RNN. The controller RNN repeats the above 5 prediction steps for each block and for each blocks in a convolutional cell. And after we select the initial hidden states in the following steps 3 and 4, the controller selects an operation from an operation list to apply to the hidden states. And this list contains many prevalent convolutional or deep learning layers, such as the separable convolutional layer, which did the same effect as normal convolution, but with less parameters. And after the controller applies the operations, it will add or concatenate the two states in the final step to produce a brand new hidden state. Then the algorithm appends the newly created hidden state to the existing set as a potential input in the later subsequent blocks. Finally, the system concatenates all of the unused hidden states generated in the later cells to provide the final cells output, which is the final output of this whole system. NASNet makes the controller have 2 times 5 B predictions in total, allow the controller RM to break the both normal cells and the reduction cells separately. NASNet uses the same reinforcement learning proposal in NNS, which will reinforce with baseline to optimize the controller. However, it is also possible to use a random search approach in both NASNet and NAS search spaces. In random search, instead of sampling the decisions from the softmax classifiers in the controller, we can sample decisions from a uniform distribution. However, the randomness actually makes the results slightly worse on the CFAR10 datasets in practical. From the plotting graph, we can notice that reinforcement learning approach has a better searching efficiency. But although there is a value or advantage in using reinforcement learning, looking at the random search is still important. The gap between random search and the reinforcement learning is smaller than their previous work. And this result suggests that the NASNet search space is well constructed such that even random search can perform reasonably well. Again, there's many advantages for the NASNet, such as scalable to different image datasets, and it has strong transferability in experiments. However, the main problem, I think, is still the high computational cost for training. During the training experiments, the pool of workers in a working queue consists of 500 GPUs. The result of this search process over 4 days procedure and produce several convolutional cell candidates. This search procedure is almost 7 times faster than the previous one. But I think still the number of GPUs for training will constrain the application or the generalizability of the NASNet to other different texts, not just convolution or probably other computer science areas such as computer graphics. Now let's look at the results of the NASNet. Here's the example of the best architecture of convolutional cells in the CFAR10. In the table, the NASNet A, B, C means different best 3 convolutional cell structures. The number before the X sign indicates the number of cells repeats, and the later one indicates the numbers of the filters in the layer before the final output layer. From the table, you can see that even a large NASNet A model with cutout data augmentation achieves 2.4 error rate, which is slightly better than the previous best score. And table 2 shows that the cell structure learned on the CFAR can be well generalized to the ImageNet. And you can see that the number of parameters are dropped dramatically in each group with different input size. Each model based on the convolutional cells in the NASNet exceeds the predictive performance of the corresponding human design models. This is a complete summary of NASNet results in comparison with other published results. You can clearly see that the group of NASNet solutions has better accuracy, but also less parameters and the multi-add operations. And also the author states out that the NASNet achieves a better accuracy than MobileNet and ShiftNet on the in-part computational resources to prove that the NASNet is applicable to the mobile devices. Image classification networks provide generic image features that may be transferred to other computer vision problems. One of the most important tasks is the spatial localization of the image within of the objects within an image. The researchers plugs in the NASNet pre-trained, which is pre-trained on the ImageNet, into the fast RCN object detection pipeline. The system achieves an MAP score of 29.6% for the mobile optimized network, which is the input resolution is 600 times 600. The ResNet exceeds the previous networks by over 500, and also for the 800 times 800 input images, the NASNet achieves MVP scores equal to 40.7%, exceeds the equivalent object detection system by 4%. These results provide further evidence that NASNet provides superior generic image features that may be transferred across other computer vision tasks. Thus, in this work, the team from Google demonstrates how to learn scalable convolutional cells that transfer to multiple image classification tasks. In all cases, the accuracy of the resulting model exceeds all human-designed models. The key contribution here is to design a search space that decouples the complexity of the nowadays networks architectures. This resulting search space permits good architectures on a small dataset and can transfer the learned cells to the image classification across a range of data and computational scales. For the possible future work, the paper didn't mention any directions, but I believe one direction is that we should further decrease the required training cost and computation cost to achieve a better result on the mobile devices, and also try to investigate more applications. Also, I think we can apply this method to the autoencoders, but the paper did not mention anything about upscaling convolutional cells, which is required by autoencoders. I think autoencoders are prevalent, especially for the 3D data learning, such as medical images and the 3D geometry for the 3D graphic models. The 3D data has more applications, especially in the VR and AR devices, but much harder to learn because of the large input data size. So I think the NAS type approaches may be a very reliable helper for the 3D data learning problems. This is the end of my presentation. Thank you.